Okay, so continuing with the chapter of stoichiometry and all the talk about moles. Right, first of all, yesterday we did some questions about finding the number of atoms in a certain number of moles and also the mass of product produced when you have a certain mass of reactant, and right, what mass of a chemical corresponds to the moles of that chemical used. Right, we came across equation 1 of formula 1, which is number of moles is mass of element over molar mass, which is either the relative atomic mass or relative molar mass, depending on whether you're dealing with an element or a molecule. Right, then we have mass of a compound is number of moles times the molar mass. Right, so we did questions relating to that. Then we talk about moles and gases, and so gases, 1 mole of gas at RTP occupy 24 liters or 24 decimeter cubes. So decimeter cube is what's used. 24 decimeter cubes of volume at RTP, and so whatever gas it is, 1 mole of that gas will occupy that volume, and because it's 1 mole, there will be 6.02 into 10 to the power 23 particles of that gas. And so equal volumes of gas at RTP have the same number of particles. That is Avogadro's law. For that, we have the equation number of moles of gas is volume of gas in dm cube at RTP divided by 24 dm cube. Right, and you can flip that around and get the other variants depending on what the subject is, what the unknown is. Did a couple of questions for that. And so today we are moving on and we'll talk about moles and solutions. Right, so we have come across solutions, right, all the aqueous chemicals, the acids and the bases and stuff. And so what we want is to, right, perhaps make a solution of a certain concentration, right? So I want a certain mass, a certain amount of a chemical in the solution, right? It's not like adding tea to sugar, where it's like, okay, fine, just 2 heapfuls of sugar, right? And that's it. We want to be precise. And so the concentration, right, can be given as the concentration of a solution can be given as grams per decimeter cube, right? And so a decimeter cube is a liter, so it's grams per liter, but we use decimeter cube in science, chemistry at least, but it is more convenient, right? And more often it is given as moles per decimeter cube. And so when you know moles, I mean, when you know the mass, you can calculate the moles. When you know moles, you can calculate the mass. It's more about, a convention. So this is more often how you would come across concentration. Okay, now what do we do? Here we come across formula number 4. And remember, when talking about solutions, we are talking about liquids, right? So aqueous, chemicals in water. And so you've got to find the concentration right, in mole per decimeter cube. You do number of moles, which you can find from the mass that you're using. So using one of the formulas we've done back here, right? Number of moles is mass of elements over molar mass, and you find the number of moles. If they haven't given it to you, if they give you the mass, you need to work from that point over the volume, right? And the volume should be in dm cube, so it should be in liters, which, right, makes it easier. It's not in like, oh, it's 500 ml. No, 500 ml is 0.5 dm cube. So that's what we do. Oh, by the way, right, instead of ml, what you'll be given is centimeter cube. So basically, right, 1 ml, which is the kind of volume we are used to, is equal to 1 centimeter cube, right?
Yeah.
And so 1000 ml equals to 1 liter, right? Which is also 1, because 1 ml is 1 centimeter cube, which is 1000 centimeter cube, which is, can also, instead of writing 1000 centimeter cube, you write 1 decimeter cube. So just the relation over here, right, is what you'll come across is either centimeter cube if you're dealing with quantities, volumes less than 1 liter or 1 decimeter cube, and if you're going above that, then you'll have decimeter cube. So you could have 500 centimeter cube, or 250, or 200, or 125, or some whatever. And so you need to convert that into liters. And basically what you do is, for example, if you have 180 centimeter cube, and so what's that in liters, you divide by 1000 and you get 0.18 decimeter cube, right? So that's how you get the volume in decimeter cube. Okay.
Yes.
Okay. Now obviously, right, you can move the equation around to get what you want, and so you can find the number of moles by multiplying the concentration in mole per decimeter cube by the volume in decimeter cube. Right, volume in solution, as the book says. The same thing, right? It's using it as you need. So let's do questions based on this, shall we?
Yeah.
Also on a side note, well, not a side note, very much on the front note, right? If you have, for example, you have 1 mole of a substance in 1 liter or 1 dm cube, then the concentration will be 1 mole per dm cube. And similarly, right? So what we're doing over here. But let's take a look at that in terms of solving problems. So the question we have is to calculate the concentration of a solution of sodium hydroxide. So what is the concentration, just writing that, of sodium hydroxide? That is what we want to find. which was made by dissolving 10 grams of sodium hydroxide. So you took 10 grams of NaOH and you put that in water up to 250 cm cube. Right, and so first of all, as like we got 10 grams, and so what is, right, how many moles is 10 grams? So 10 grams in moles, right? And so first of all, we need the MR of NaOH. And so sodium is 23, oxygen is 16.
And hydrogen is 1.
Yes, and that gives us,
Uh, 40.
yep. And let's say 1 mole of NaOH is 40 grams, right? So this is 1 mole. And so number of moles of NaOH used equals to 10 over 40, which equals to 0.25.
Yeah. So there are 0.25 moles in 10 grams of NaOH.
Right? Next, we have 250 centimeter cube, and we need to convert that to dm cube. So what we're going to do is divide that by 1000, and that gives us 0.25, right? dm cube. Now to apply the formula, right? Concentration is number of moles over volume. So concentration equals to 0.25 moles over
Volume
0.25
would be
dm cube.
constant.
Hmm?
Volume would be constant.
No, volume would be as much as you're using or you're making in this question, right? And so that actually comes up to 1 mole per dm cube, right? Now you'd say, well, they could have just taken 40 grams and put it into 1 liter. Yes, but the thing is that you don't want a liter of sodium hydroxide. Okay, so when I'm working in the lab and I've got like anhydrous sodium hydroxide, so it's powdered, right? And I want only 250 ml for my titration experiment, for example, right? Which we'll talk about after this chapter. I don't want a liter because it's going to be left and it might spill or whatever. It's going to go to waste, and sorts of that's resources going down the drain. And so I need to calculate what mass of sodium hydroxide I'm going to use for 250 ml only to get 1 mole per dm cube. Right, so I'm getting that same concentration that I would have gotten if I added 40 grams into a liter of water. But this time I'm adding only 10 grams in 250 centimeter cube of water. Make sense?
Yes.
Right? So having 1 mole per dm cube, right? That is your answer. Next question. Right, you need to calculate the mass of potassium hydroxide used. Mass of potassium hydroxide used to prepare 500 centimeter cube. So you got 500 centimeter cube volume, and the concentration is 2 mole per decimeter cube. 2 mole per decimeter cube volume, right? And so what do we have in the equation back here? Number of moles equals to concentration times volume. Right, so as far as the volume is concerned, 500 cm cube divided by 1000 is 0.5 dm cube. And so number of moles of KOH used, I'm just writing that to clarify, equals to 0.5 into 2, right? Which gives me 1 mole.
Yeah.
Which basically means all I need is the relative molecular mass of QH. So let's take a look at that. We could obviously use the formula back here, right? That's something that you want. So mass of compound, use that. What we want is number of moles, which is 1 times the molar mass. So basically what we want is the molar mass, because this is 1, so that's not going to affect anything. So molar mass of compound is the mass of compound used,
Okay.
right? And so MR of potassium hydroxide is, potassium is 39
39
plus 16 plus 1, so that
plus 1.
gives me 56
6.
grams, right? And so, right, I'm adding a full molar mass in half the volume. I say half because we're using half a liter, and so that gives me a concentration of 2 moles per decimeter cube. It is equivalent to adding 112 grams in 1 liter.
We will be given the molar mass, no?
You will be given the periodic table,
Okay.
right? And so
And
you
that
take,
it is
yeah, so the periodic table has the individual relative atomic masses of the elements, and so you just say, okay, what's the right? KOH is the chemical formula for potassium hydroxide, right? Just like we wrote NaOH or anything else. And so I take a look at, what the relative atomic mass for potassium, for oxygen, and for sodium, and I put those together, and I get, right. So it possibly could be given to you, but if they're trying to check whether you know how to figure it out, then this would be a 1 mark question, or maybe a 2 mark question.
Okay.
Okay.
Yeah. Let's do another question.
uh
Or we ran out of questions.
I mean, those are all the worked questions that we had. If you want to do another one for solutions,
Okay.
let me see. Okay, here's one. All right, so this is from the test yourself questions in the textbook. Uh, First, calculate the volume of 0. No, but this looks like it's talking about gases. So it's carbon dioxide, hydrogen, chloride. No, sir. Let's look at the other one. Calculate the concentrations of, so you need to know the concentration of uh, 0.2 mole of sodium hydroxide, and the volume given, dissolved in water and made up to 100 centimeter cube, right? So it's 100 centimeter cube, and you need to know the concentration, right? And so, right, the 100 centimeter cube becomes 0.1 decimeter cube. So going back, Concentration is number of moles over volume in dm cube. And so we concentration, you probably write the whole thing. It's 0.2, so number of moles multiplied, divided by 0.1, and that gives me 2, right?
Wait. Yeah, 2.
Yeah, so number of moles divided by volume, and that is 2 moles per, so this is mole and this is dm cube, so you get mole per dm cube. Now it's simple,
Yeah.
right? How did I get 0.1? 100 divided by 1000.
Okay. Yeah.
Then, yeah, I mean, there's another one, but it's pretty much the same thing. It's pretty simple.
Yeah.
So these test yourself questions are pretty straightforward.
Okay.
Okay, now comes a part which is slightly tricky. And that is figuring out or calculating formulae based on molar ratios. So I explained to you guys yesterday when we looked at, where's that equation? Yeah. Right, sodium reacting with water giving you sodium hydroxide and hydrogen. Right, the equation at the top of the page. And so, right, we talked about atoms and molecules reacting together, but again, we're not dealing with individual atoms and molecules. And so we refer to that as moles, right? So 2 moles of sodium reacting with 2 moles of water, giving you 2 moles of uh, sodium hydroxide and 1 mole of water. Sorry, hydrogen, not water, hydrogen. Right, and so when you, right, this is tells you the importance of a balanced equation. So all the balancing that we've been practicing, we have, right? Have we not?
Yeah.
Right, so the importance of balanced equations and correct chemical formula. So knowing the oxidation numbers and, at least knowing the crossover method. So an example obviously is 2Na plus 2H2O giving me 2 NaOH and H2. Right, so that is a balanced equation. And knowing the correct chemical formula, for example, you've got sodium carbonate. Right, so what's sodium carbonate? So I know sodium has an oxidation number of +1, and the carbonate ion has an oxidation number of 2 minus. And so using the crossover method, right?
And A minus 2 and CO plus 1?
What?
Crossover, right?
Yeah, but the numbers are going to come as a subscript, right? So you need 2 atoms of sodium to react with a single carbonate ion. Two ions of sodium to bind
Can you,
to a single carbonate ion. So the
can you
formula for
explain that
sodium
again?
carbonate is Na2CO3. Yes, Saran?
Can you explain that again?
I think we're cross multiplying, right?
Yes, that, like, call it crossover method, but that's basically what it is.
Okay.
Okay, experimenting again. Haram, going back. Right, for example, we've got iron, right? Iron 3. So it is an oxidation number of +3. and we've got sulfate, right, which has an oxidation number of 2 minus, right? And so if you're asked what is the, you know, chemical formula for iron sulfate, now in case of iron sulfate, because it has a variable oxidation number, they will give it to you as iron 2 or iron 3, right? So they'll give it to you as Roman numerals. And so in this case, I'll ask you what is the chemical formula for iron 3 sulfate. The fact that I said iron 3 sulfate tells you that the oxidation number of iron is 3, right? You need to know the oxidation number of sulfate, and that's 2 minus. So how do you figure out the chemical formula? This is not the textbook says it's not a scientific approach, sure, but does it help? Yes. And so you take the oxidation numbers and you sort of cross multiply, as Sobia said, right? And so what that would mean, because the oxidation number of sulfate is 2, what I would be needing to make iron 3 sulfate is 2 ions of iron, that's Fe2 coming from the sulfate. Now for the 3, because this is a complex ion or a molecular ion, don't multiply 3 with the 4 on the oxygen and say it's SO12.
Then what?
Like, can we won't write the 3
We
and
would.
like negative 2?
No, we won't put this negative. The negative and positive basically tells us that iron is losing electrons and the sulfate is gaining electrons.
Okay. Yeah.
Sophia, you sound confused. This is from way back
No, no,
when.
no, no, no. That I'm just saying. I'm agreeing with you.
Right? So what you do is SO4 stays as SO4 and you put it in brackets and then you write 3 outside the bracket, which means you need 3 sulfate ions to combine with 2 ions of iron 3 to make iron 3 sulfate.
So like then we won't write the positive 3 at
No,
the
no,
top.
no, no,
Like
no.
that will
That is
put.
only to show the oxidation number or the ionic state. Combined as a compound, it's not in its ionic state. Okay.
Yeah.
Another example, since we're talking about this, right, is for example copper 2 nitrate. Oh, you got a copper 1 nitrate as well, but let's keep it interesting. So copper 2, right? Copper can be either copper 1 or copper 2. So we're talking about copper 2. And so when I say copper 2, it's a metal. And so metal lose electrons. So there's an oxidation number of 2 and it's plus. Nitrate has an oxidation number of -1. Right? So what would the chemical formula of copper 2 nitrate be? Haran?
Yeah.
What would the chemical formula for copper 2 nitrate be?
Uh, copper nitrate 2.
Copper nitrate 2?
Like we will write copper.
You say Cu. You don't say copper, you say
and
Cu
and put a bracket
bracket
and then nitrate 3, NO3,
NO3.
and then 2 after the bracket.
Good.
Yeah.
Right? Copper 2 nitrate. All right. Okay. So talking about chemical formula, calculating formula, sorry. In fact, if I just take you to the book for this one, for the explanation. Can you see that?
Yes.
So if we have 1 mole of a compound, then the formula shows the number of moles of each element in that compound, right? For example, lead to bromide. So again, lead to bromide, so you can figure it out. Bromine has an oxidation number of -1. Since it's lead 2, that is +2, and so what we're going to get is PbBr2. Now, right, what that tells us, and the reason why I was making you practice chemical formula, proper chemical formula, is, right, this tells us that 1 mole of lead to, 1 mole of lead to bromide contains 1 mole of lead ions and 2 moles of bromide ions. Does this make sense?
Like moles means
Moles,
2 BR
mole means mole,
or
right?
like BRC.
1 mole is 6.02 into 10 to the power 23. So, right, it contains 2 moles of bromine ions.
Like it will be written as 2BR or BR2.
Br2,
Okay.
right? So, quickly taking you back on that note to the whiteboard, and then we'll come back here. Where is Google Meet? This is the annoying part, is I have to keep individually switching through windows. Right, so if you take a look at this, we take a look at water, and so based on what we just read, water has 2 moles, right? Forget the 2 over here. Let's just take a look at the formula for water, right? H2. So that's 1 mole of water. Within 1 mole of water, right? Within 1 mole of water, you have 2 moles of hydrogen ions and 1 mole of oxygen ions. Right?
Yeah. Okay.
In NaOH that we have in that equation, you have 1 mole within the molecule itself, for the compound itself, right? So what we were talking about was as an equation as a whole, but within that you have 1 mole of sodium ions and 1 mole of hydroxide ions, right?
Yeah.
Sodium is sodium, hydrogen, right? So this is H2 is 1 mole of hydrogen gas, right? Or hydrogen molecule, because it's diatomic. Over here, you've got 2 moles of sodium ions and 1 mole of carbonate ion. I'm just putting the numbers, right? We're talking about moles. Fe2SO4 thrice. So you've got 2 moles of the iron ions and 3 moles of the sulfate. Making sense? Are you following?
Yeah.
All right. So how many moles of copper do we have in copper nitrate? Copper 2 nitrate?
Could you repeat that?
In copper 2 nitrate, can you tell me the number of moles of each constituent?
Yeah, like 1 mole
1 mole of
copper and nitrate as well.
no, you got 1 mole of copper and 2 moles of nitrate.
Like how do we have 2 moles of nitrate? It's
And
one
for
mole.
oxygen, we have 6 moles.
No, 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 no. You're dealing with nitrate as a complex ion. So we're not going into that. Yes, within the nitrate you can talk about 1 mole of nitrogen and 3 moles of oxygen, but we're not talking about that. We're dealing with nitrate as a complex ion as a whole. So how do we have 2 moles of nitrate? Because of the bracket beta.
Outside the bracket, we have 2.
Inside the bracket we've got, right, so out it gives 2, and so that means you've got 2 of these guys. Just like I put 3 for SO4 over here.
So like we have moles of oxygen.
Huh?
Or so like we have 4 moles of oxygen.
If you want to look at oxygen independently, then overall you've got 6 moles of oxygen ions. Oxygen ions,
Okay.
right? Not
Yeah.
not oxygen gas. Oxygen ions.
6.
6. 2 times 3 is 6.
Oh yeah. Sorry.
Okay. Back to the book. So if we do not know the formula, now this is right. So the subheading is calculating formula. So what if I don't know the formula? Can I use masses and moles to figure it out? We can find the masses of the elements present experimentally, and we can use these masses to work out the formula of the compound. Okay, how do we do that? I've done this in a lab way back when, right? And something even more advanced than that. So they go through this with a worked example, and so that's what I'll share with you. So in an experiment, can I zoom in further? Yeah. So in an experiment, an unknown organic compound was found to contain 0.12 grams of carbon and 0.02 grams of hydrogen. Okay, and so you make a table over there, right? You've got, and those are the only two compounds, like elements you have in the compound, right? So you put carbon, hydrogen, those are the elemental symbols, and the masses were 0.12 and 0.02, right? Calculate what is called the empirical formula of the compound, right? So the empirical formula is the minimum ratio of the atoms of the elements in the compound. So what are we doing, right? The mass is 0.12 for carbon, so we find the number of moles of carbon, and that's 0.01. And similarly for hydrogen, right, at 0.02. And then we get a ratio, right? So it's 0.01 to 0. So the number of hydrogens is twice the number of carbon. So the ratio of carbon to hydrogen in this organic compound. And see, I feel it's a good thing that we're coming to this chapter at the end. If I would have done this in sequence, then it would have been relatively much more challenging to grasp. Do you feel that? Do you guys feel that way?
Yeah.
Hmm. Okay. So you got the ratio 1 is to 2, and so the empirical formula, which as I said, is the minimum ratio of the atoms of elements in that compound. So it's CH2. Now the problem is we know that there is no CH2, right, in any organic compound, right? CH2 by itself is nothing. So from our knowledge of covalent bonding and organic chemistry, we know that a molecule of this formula cannot exist, right? Because carbon makes 4 bonds, it can only make a single bond with hydrogen, it's not making double bonds with hydrogens, and so it is lacking 2 bonds. However, molecules with the following formula exist. So you've got CH2, so you've got C2H4, C3H6, C4H8, C5H10. What molecules are we talking about over here? They're not mentioning it. What homologous series is this from? CnH2n. General formula CnH2n.
Alkali.
Huh?
Alkali. Alkali.
Alkali
Um,
is
sorry. Alkaline.
okay. Alkali and alkaline have nothing to do with organic molecules.
Like we did
We
C
did
and
we did alkane, alkene, alcohol,
Alkene, I don't know how it's pronounced, but it's Alkenes.
alkenes.
Yeah.
Yeah, so these are alkenes.
Yeah. Okay.
Okay, right? Now all of these have carbon hydrogen in the same ratio, right? CnH2n. So that's C. If C were 1, H would be 2. Of course, we don't have a methane for the reason because that carbon can it's lacking double bond. Okay, so you can so what this means is that the CH2, because it's showing the ratio only, and so it could be any one of these guys. So all of these formulas show the same ratio of carbon to hydrogen atoms, CH2, as what we've concluded based on the information we had. And so we take the calculation further. To find out which of these formula is the actual formula for the unknown organic compound, we need to know the molar mass of the compound. Okay, so what's the molar mass of the compound we have? And so, right, that is done using mass spectrometry, which is not in your syllabus, right? You will come across it in A level if you choose to take chemistry. And so we figured out using a mass spectrometer that the relative molecular mass of this compound was 56, right? So how do we use that? So we know that the relative molecular mass is 56. And what is the molecular mass for the empirical formula that we figured out, right? It's CH2, so carbon is 12, 2 of hydrogens, and you get 14 in total, right? And so what you do is you divide the molecular mass of the compound by the mass of the empirical formula unit, because again, CH2 itself is not the chemical we want. It's just a ratio of the carbon to hydrogen. So 56 divided by 14 gives us 4, right? So there are 4 CH2s in this compound. And so what we do is we multiply CH2 by 4, and so we get C4H8, which is, what's the name of this guy?
Which one?
C4H8.
which one?
Here, C4H8. You guys can see the book, right?
Alkene.
Huh?
Alkene.
Alkene is the homologous series.
Okay.
Specifically, C4H8.
Butene.
Butene. Butene.
Methane. Oh yeah. Sorry.
Butene. Right? I mean it's written over here. The substance is called butene. C4H8 is the molecular formula for the substance and shows the actual numbers of atoms of each element present in one molecule of the substance. Okay?
Yeah.
Yeah.
Now we are just about out of time. Can we manage this? I think we should do this since we have discussed everything else. I don't want to leave it for next class because I'm pretty sure by then we'll forget. Now I am working with the worked example. I hope you haven't peeked at it. Don't peek at it while I change screens. I'm going back to the whiteboard. Okay. So the question is that you need to calculate the empirical formula for an organic compound containing 92.3% carbon and 7.7% hydrogen by mass. Now they're given percentages. How do we deal with percentages? So carbon is 92.3. Yeah. 92.3%. Hydrogen is 7.7%. And what we need is the they've given the molecular mass of the organic compound to be 78, right? So Mr equals to 78.
And
And
what do we find?
so first of all, we need the empirical formula.
Like we will round that up.
Huh?
We will like round up
Oh no,
the numbers.
not at all. Not at all.
Imperial
Em,
formula for what?
empirical. What we
Empirical
what we need is the molecular formula. What they're asking is for the molecular formula.
for CNH, right?
Yes, for the, well, not for CNH, but for the organic compound that has carbon and hydrogen in these ratios, right? So first of all, we find the empirical formula for that, right? You put in the headings carbon and hydrogen, and what you do, right? First of all, you write the percentage by mass, and so 92.3, sorry, not 92.3% by mass is carbon, and 7.7% by mass is hydrogen. And what we do is like, okay, fine, we're talking about percentages, right? And so let's take mass in 100 grams. And so that means in 100 grams of this substance, you're going to have 92.3 grams of carbon and 7.7 grams of uh, hydrogen. And that makes it easier.
Yeah.
That makes it easier because now we have actual weights to deal with. And so what we do then is find the number of moles,
Okay.
right? So 92.3 divided by 12 and
Gives us 7.69.
7.7.
Okay.
Are moles given?
Hmm?
Like they have given the moles in question.
No, we are calculating it right now.
Okay.
Right now, you would ask, well, if you're assuming 100 grams, wouldn't that affect our calculation? No. Why? Because we're finding the number of moles and then we're going to take a ratio of that mole. So the ratio is going to be same whether you've got 1 gram, 100 grams, or 1,000 grams. Right?
Yeah.
So number of moles of hydrogen is 7.7 over 1, which is 7.7. And so the ratio is 1 is to 1. Sorry, not C and H, is 7.7 and 7.7. So the ratio is 1 is to 1. So you've got an equal number of carbon and hydrogen.
And the empirical formula is CH.
Yes, and so good. So the empirical formula is CH. Now we know that this cannot be the molecular formula because you don't have anything that is like it. And so now we go and we say, okay, what is the mass? And so this is 13 for this guy. We have the mass over here. And so what we're going to do is we're going to uh, find the number of empirical units present in the compound. So number of empirical formula units in compound. And so we're going to do 78 divided by 13, which gives us 6, right? Which means, right, there's 6 of these CH guys in the compound. So I'm going to get C6H6. And that is the molecular formula. Now you'd be like, well, that's odd. We haven't studied that. Yes, you haven't, because this is something I did mention this when we were doing
Oh,
esters.
benzene.
Benzene, yes, right? Benzene will be your favorite organic compound in A level chemistry and perhaps beyond if you decide to pursue organic chemistry later on or you're forced to take it. But this is a compound called benzene.
And how do we know the name?
Because I just told you.
Like, yeah.
Okay, I mean, they won't ask you to name it. They won't like that. That's not
Okay.
the question. The question is just the molecular formula, right? So if you've done your working correctly and you come up with something like this, don't be confused like we haven't learned that, it can't be correct. No, if your calculation is correct and this is what you're getting, that's what it is. You don't need to worry about I don't know this. Fine, you don't, but is your calculation correct?
Yeah.
Okay.
Yeah.
Can we do another
And
question?
huh?
Can we do another question?
Oh, you're having fun.
Yeah.
Unfortunately, I have another class.
Oh, yeah. Okay.
Right. Okay. So we could try and do some. There are test yourself questions. Remind me next time if I don't, have that in mind, and we could start off with some questions.
Okay.
Okay. All right. I'll see you guys next time, inshallah. Hope everything was clear
Sure.
today.
Yeah. Okay.
Okay. And glad to know you were having fun. That is the highlight for me. Okay. Allah Hafiz.
Mhm.